13.4 Kepler's laws and the motion of planets. The outline of this video is as follows. We will start by setting the stage, exploring some of the early historical models that humans developed to describe the solar system, such as the geocentric and heliocentric views. This historical context is essential for appreciating the breakthrough that followed. The core of our discussion will then be Johannes Kepler's 3 fundamental laws of planetary motion, which provided the first accurate mathematical description of how planets orbit the Sun. To properly understand these laws, especially the first one, we will need to review the specific geometric properties of elliptical orbits. Finally, we will see how to apply this knowledge. We will use Kepler's laws, particularly the third law, to perform calculations for orbital parameters and even determine the masses of celestial objects like planets and stars. To understand Kepler's laws, we first need to appreciate the historical context that led to their discovery. For over 1400 years, the dominant scientific view was the geocentric model, championed by Ptolemy, which placed a stationary Earth at the center of the universe. In 1543, Nicolaus Copernicus challenged this idea with his heliocentric model, correctly placing the Sun at the center, but incorrectly assuming the planets moved in perfect circles. The critical next step required moving from philosophical models to precise, data-driven science. This was the contribution of Tycho Brahe, who, without a telescope, compiled the most accurate and comprehensive astronomical observations of his time. After Brahe's death, his assistant, Johannes Kepler, inherited this invaluable data. He spent years performing meticulous calculations to find a mathematical description that fit the observations, especially for the orbit of Mars. This painstaking work of matching a mathematical model to real-world data is what ultimately produced Kepler's 3 foundational laws of planetary motion. Johannes Kepler fundamentally changed our understanding of the solar system by summarizing his observations into 3 elegant laws. These laws describe the motion of planets with remarkable accuracy and moved us away from the ancient idea of perfect circular orbits. First is the law of orbits. It states that all planets move in elliptical paths, not circles, with the Sun located at one of the 2 focus points of the ellipse. Second, we have the law of areas. This law tells us how a planet's speed varies during its orbit. A line drawn from the Sun to a planet sweeps out equal areas of space in equal intervals of time. This means the planet moves fastest when it is closest to the Sun and slowest when it is farthest away. Finally, the third law is the law of periods. It provides a precise mathematical link between a planet's orbital period, which is the time it takes to complete one orbit, and the size of its orbit. The law states that the square of the period is directly proportional to the cube of the semi-major axis of its orbit. Together, these 3 laws form the foundation of our understanding of celestial mechanics. Kepler's first law reveals that the paths of planets are not perfect circles, but rather ellipses. This was a major shift from earlier models of the solar system. An ellipse is a specific geometric shape defined by 2 points inside it, called foci. For any point on the ellipse, if you add the distances to the 2 foci, that sum is always a constant value. We describe the size of the ellipse with the semi-major axis, which is half of its longest diameter, and the semi-minor axis, which is half of its shortest diameter. Here is the most important part. The Sun is located at one of the 2 foci of a planet's elliptical orbit. It is critical to remember that the Sun is not at the center of the ellipse, and the other focus is simply an empty point in space. So the key takeaway is that planetary orbits are ellipses, with the Sun positioned at one of the 2 focal points. Now let us introduce a single number, called eccentricity, that precisely describes how non-circular an elliptical orbit is. Eccentricity, represented by the letter E, is defined as the ratio of C over A, where C is the distance from the ellipse's center to A focus, and A is the semi-major axis. For any ellipse, the eccentricity is a value greater than or equal to 0 and less than 1. A perfect circle has an eccentricity of exactly 0. As the ellipse gets more stretched out, its eccentricity gets closer to 1. To get a feel for this, Earth's orbit is nearly circular, with an eccentricity of only about 0.017. Mercury has the most eccentric orbit of any planet, at 0.21. In contrast, Comet Halley follows a highly elongated path with an eccentricity of 0.97. This shape determines the points of closest and farthest approach to the Sun. The point where the planet is farthest from the Sun is called the aphelion, at a distance of a plus c. The point where it is closest is called the perihelion, at a distance of a minus c. Therefore, eccentricity is the key parameter that quantifies an orbit's shape and sets the minimum and maximum distances from the Sun. Let us now examine Kepler's second law, which states that a planet sweeps out equal areas in equal time intervals. This observation is not just a geometric curiosity, it is a direct consequence of the conservation of angular momentum, a fundamental principle of physics. To understand this connection, we first need to characterize the gravitational force. The force the Sun exerts on a planet is a central force. This means the force vector always points directly along the line connecting the two bodies, which is parallel to the planet's position vector, r, as measured from the Sun. Now let us recall the definition of torque. Torque, represented by the Greek letter tau, is the cross product of the position vector r and the force vector F. Because the gravitational force is central, the vectors r and f are always parallel. The cross product of any two parallel vectors is 0, so the net torque on the planet is 0. Finally, remember that torque causes a change in angular momentum. Since there is no net torque on the planet, its angular momentum must remain constant throughout its entire orbit. Therefore, Kepler's second law is fundamentally a statement about the conservation of angular momentum for an object moving under a central force. Let us now formalize Kepler's second law by showing mathematically that the rate at which a planet sweeps out area is constant. This derivation directly connects the law to the conservation of angular momentum we just discussed. First, consider the small, triangular area, dA, that the planet's position vector sweeps out in a short time interval, dt. From geometry, this area is 1/2 the magnitude of the cross product of the position vector r and the displacement vector dr. Since displacement is just velocity v times dt, we can rewrite the area dA in terms of r and v. Next, we recall the definition for the magnitude of the planet's angular momentum, L. This is the planet's mass, m sub p, times the magnitude of r cross v. We can see that this cross-product term appears in both our area and angular momentum equations. By substituting the angular momentum expression into our area equation, we find that dA is equal to L divided by the quantity 2 times, m sub p, all multiplied by dt. Dividing by the time interval dt gives the final result. The rate at which area is swept, dA over dt, is equal to L divided by 2 times, m sub p. Because both the angular momentum and the planet's mass are constant, this rate is also constant. We now arrive at Kepler's third law, also known as the law of periods. This law provides a powerful mathematical link between how long it takes a planet to orbit the Sun and the size of its orbit. To derive this, we will start with a simple circular orbit. The key physical insight is that the Sun's gravitational force is the force that keeps the planet moving in a circle. Therefore, the gravitational force must be equal to the centripetal force. We express this by setting the formula for universal gravitation equal to the formula for centripetal force. As you can see in the first equation, the mass of the planet appears on both sides, so it will cancel out. Next, to bring the period, t, into the picture, we replace the orbital speed, v, with the expression for the circumference, 2 pi r, divided by the period. Substituting this for v and simplifying gives us the final equation on the slide. This equation establishes the fundamental relationship between the orbital radius and the orbital period. We can now state Kepler's third law in its full, general form, which applies not just to circular orbits, but to the more common elliptical orbits as well. The key is to replace the radius, r, with the semi-major axis of the ellipse, which is denoted by the letter A. You can think of the semi-major axis as the average distance between the planet and the Sun. With this change, the law becomes the orbital period squared equals a constant k sub s times the semi-major axis cubed. This constant of proportionality, k sub s, is determined by the mass of the central body, which for our solar system is the Sun. Its value is approximately 2.97 times 10 to the power of negative 19 seconds squared per meter cubed. Crucially, this constant does not depend on the mass of the orbiting planet. This means the ratio of t squared over a cubed is the same for every object orbiting the Sun, from the planet Jupiter to the smallest asteroids. The square of an object's period is proportional to the cube of its semi-major axis, and this relationship is governed only by the mass of the Sun. Let us analyze this question by applying Kepler's third law to compare the size of the asteroid's orbit to that of the Earth. We are told the asteroid has a period of 90 days, which is much shorter than Earth's period of about 365 days. Kepler's third law tells us that the square of the orbital period is proportional to the cube of the semi-major axis, which describes the average size of the orbit. Because the asteroid's period is significantly smaller, its semi-major axis must also be significantly smaller. This means its entire orbit is, on average, much closer to the Sun. Even though the orbit is highly eccentric, its farthest point from the Sun, called the aphelion, is still constrained by its small semi-major axis. The asteroid's aphelion distance is well inside Earth's orbital radius of 1 astronomical unit. The asteroid's entire path is safely contained within Earth's orbit. Therefore, there is no possible danger of a collision. We can now apply Kepler's third law to solve a classic problem: calculating the mass of the Sun. This is a powerful demonstration of how orbital mechanics allows us to measure celestial objects we cannot access directly. The process is a straightforward substitution problem. First, we take the equation for Kepler's third law and algebraically rearrange it to solve for the mass of the central body, which we will call m sub s for the Sun. This gives us the expression m sub s equals the quantity 4 times pi squared times a cubed, all divided by the quantity g times t squared. Next, we gather the necessary orbital data for a planet orbiting the Sun. Using the Earth, we know its semi-major axis, a, is approximately 1.496 times 10 to the power of 11 meters, and its period, t, is about 3.156 times 10 to the power of 7 seconds. We also use the known value for the gravitational constant, g. Plugging these values into our rearranged equation yields a mass for the Sun of approximately 1.99 times 10 to the power of 30 kilograms. This result shows that by observing an object's orbit, we can determine the mass of the central body it revolves around. Let us determine the speed a satellite needs to maintain a stable, circular orbit around a planet. The key physical principle is that the planet's gravitational force provides the exact centripetal force required to keep the satellite moving in a circle. We can express this by setting the formula for gravitational force equal to the formula for centripetal force, which is m times v squared over r. After solving for the speed, v, we find it equals the square root of the quantity g times the planet's mass, all divided by the orbital radius. It is important to remember that the orbital radius, r, is measured from the center of the planet, not its surface. Therefore, you must add the planet's radius to the satellite's altitude. Now, consider what would happen if the planet were more massive. The stronger gravitational pull would require the satellite to travel faster to stay in the same orbit. Our derived equation confirms this. The orbital speed is directly proportional to the square root of the planet's mass. The essential result is that a satellite's speed in a circular orbit depends on the mass of the central body and the orbital radius, but not on the satellite's own mass. Now let us consider a special case: a geosynchronous satellite. This is a satellite that appears to remain stationary in the sky from an observer's perspective on the ground. For this to happen, the satellite's orbital period must exactly match the Earth's rotational period, which is 24 hours or 400 seconds. Our calculation is a two-step process. First, we must find the specific orbital radius that corresponds to this period. We use Kepler's third law, which relates the period, the planet's mass, and the orbital radius. Plugging in the values for Earth gives a radius of about 4.22 times 10 to the power of 7 meters. This is a very high orbit, corresponding to an altitude of nearly 36,000 kilometers. Once we have this unique radius, we can perform our second step, calculating the speed. We simply use the orbital speed equation we found earlier, plugging in this specific radius. This gives us a required speed of about 3.07 times 10 to the power of 3 meters per second, or 3.07 kilometers per second. Therefore, a geosynchronous orbit requires both a very specific altitude and a precise corresponding speed. Let us summarize Kepler's 3 laws of planetary motion, which together give us a powerful framework for describing orbits. First, Kepler's first law describes the shape of the orbit. Planets travel in elliptical paths, not perfect circles, with the Sun located at one of the two foci. Second, Kepler's second law addresses the planet's speed. It states that a line drawn from the Sun to a planet sweeps out equal areas in equal time intervals. This is a direct consequence of the conservation of angular momentum and means that a planet moves fastest when it is closest to the Sun, at perihelion, and slowest when it is farthest away, at aphelion. Finally, Kepler's third law provides a mathematical relationship between an orbit's size and its duration. It states that the square of the orbital period is proportional to the cube of the semi-major axis. These 3 laws were derived empirically from observation, and Newton later showed they were a direct consequence of his law of universal gravitation. Let us pause here to apply what we have learned with a couple of review questions. First, consider a comet in a highly elliptical orbit around the Sun. Based on Kepler's laws, would you expect its speed to be constant throughout its journey? If not, think about where in its long, oval-shaped path it would be traveling the fastest, and where it would be moving the slowest. Next, let us imagine 2 satellites, A and B, in perfectly circular orbits around the Earth. Satellite A is at a higher altitude, meaning it is farther away from the Earth than satellite B. Which of these 2 satellites would have the longer orbital period, taking more time to go around once? And, perhaps counterintuitively, which satellite is actually moving faster? Take a moment to think through these scenarios. Try to explain your reasoning using the physical principles and equations we have just discussed for orbital motion.